Hello pre-calc, welcome back. Our objective today is going to be to graph parametric equations by hand and on a graphing calculator. I've got the checklist on the screen. Please double check to make sure everything is ready to go and then hit continue when you are ready to continue. So first, just a little intro on parametric equations, like what are they and how are they different from what we've done before? Well, before you've been looking at rectangular equations, like y equals x squared. So these are equations that describe position only, and typically it is how your y coordinate depends on your x coordinate. So one way is to plot points, pick some values for x, find their corresponding y values, and plot them, connect those dots. So now we're going to be looking at parametric equations, and you don't need to write any of this down. We're just doing a little intro, and then we will do some examples together to solidify this idea. But parametric are equations that describe position, both your x position and your y, so horizontal and vertical, in terms of some parameter, which is typically t for time, okay? So here we've got that parametric equations introduce a third variable, also known as parameter, which in the example I have on the screen, that parameter is t. So parametric equations are useful in modeling what we call curvilinear motion. So that describes the path of some object in terms of space and time. So your position, again, your x and your y in terms of time. So you can see here that my x coordinate depends on time as well as my y. So here is the first thing I would like for you to write, and then we're going to try some examples. So please write this: orientation of a curve results from plotting xy points based on increasing values of t. So I'm going to force a pause on your screen, make sure you've got that written. So let's try a little preview of a problem here, a little warm-up problem. It says define the path of the object and describe orientation. Remember, that is what we get from points based on increasing values of t, given these parametric equations. So I'm going to force a pause on your screen. I'd like for you to copy this, these equations, this x and this y, and then make a table for me as well. All right, we are back. So it says that we need increasing values of t. Typically, we only deal with positive time values. So what I'm going to do is let t go from 0 to 3, increasing in integers. And then all I'm going to do is plug these t values in to this set of equations here. So when t is 0, what is x? X is 0. And what is y? Y is 1/2 times 0, which is 0. So I'm going to start by plotting that point. So 0, 0. All right, now let's plug in 1 for t. So when t is 1, x is 1. And when t is 1, y is 1/2. So now I'm going to go plot the point 1, comma 1/2, right about there. All right, now let's let t be 2. So when t is 2, x is 2 and y is 1. So I'm going to plot the point 2, comma 1. And then my last point that I picked, I mean, we could keep going. I just want to kind of see the pattern, see if I can figure out the graph here. When t is 3, x is 3 and y is 3 over 2, also known as 1.5. So I'm going to be right about there. And so we went green, red, blue, purple, right? So you can see if we're using positive time values, we are going kind of like this. And it did say to describe orientation. So again, that is just the direction. And that's what's new with parametric equations, is now that I have direction to my path, right? So it's not just kind of this stationary path, not just this line. I know which way the line was going. All right, I'm going to force another pause on your screen. Can you please copy x and y equations here? Then we're going to work example 1 together. We are back. So for example 1, it says eliminate the parameter t. So what we're trying to do is we have a parametric equation or a rectangular equation right now? We have a parametric equation, okay? And what we're trying to do is get this down to a rectangular equation that we recognize and that we can graph, okay? So our strategy here is going to be to get t by itself. So solve for t in this first equation. Sorry, and then do a substitution, okay? So if I want to get t by itself in that top equation, what would we do to both sides? We're going to square both sides. So if I square the left side, I'd get x squared. If I square the right side, I would just get t. Okay, and now I'm going to make a substitution. So I'm going to come to my y equation here, and anywhere I see a t, I'm going to replace with what? With x squared. So I'm going to end up getting y equals 1 minus x squared. And now I've eliminated my parameter t. Do you see that? So now we've got just x and y, which is what we're used to, again, with rectangular equations. So now let's think about how do we graph this? Think about back to Algebra 2, like what's your parent function? What transformations have we done? So our parent function is x squared, whose graph looks like what? Looks like a parabola. And this negative is going to be a reflection. Will that be a vertical reflection or horizontal? That's outside the parent function, so that'll be a vertical reflection. And then what does this 1 do? The 1 shifts it up 1 unit. So I've got my parent function reflected vertically, shifted up 1. So it would look kind of something like this if I were graphing all values of t. But again, typically I'm going to graph only positive time values. So if t is 0, let's start there, let's start our initial time, then I would have the x coordinate be 0 and the y coordinate would be 1, so I'd be here. And then when time is 1, my x coordinate would be square root of 1, which is 1. Y would be 1 minus 1, which is 0, so I would have the point 1 comma 0, and so on and so forth. So I can see, oh, I'm getting the right branch of that parabola. Okay, I want to show you how to graph these on Desmos. All right, so if you want to check on Desmos, what you're going to do is type in the equations like you would in ordered pairs. So start with open set of parentheses, and our x was equal to square root of t. And remember, to get square root on Desmos, you just can type sqrt, and it turns into a square root. So I'm going to do square root of t for my x coordinate, then arrow out of that, comma, and then my y coordinate, if we come back over here, was 1 minus t. So I'm going to go 1 minus t in parentheses, and you can see kind of the start of the parabola. The default domain on Desmos for your time is 0 to 1. If I want to continue that parabola to find the orientation, again, I can just do increasing values of t. So I can go 0 to 2, 0 to 3, 0 to 4, and I can see kind of the path or the orientation of the curve that way. All right, I'm going to force a pause on your screen. Can you please try example 2 on your own? Hit continue when you are ready to see the answer. All right, so for our final answer, we should have gotten y equals the quantity x plus 2 squared. So I added 2 to both sides here to get t by itself, and then I made that substitution, and I just left it in factored form because this shows me that it is your standard parabola shifted to the left 2. And again, I just took the right side, the right branch, because we are using positive time values. And again, we can check here on Desmos. So right now I'm just graphing from time 0 to 1. As I increase my time values, I can see the orientation of the curve. All right, so for example 3, I'm going to force a pause on your screen. Just copy again the parametric equations, and we're going to work this together. So you may notice that there's a couple differences here. First of all, our parameter is theta, to emphasize that we're looking at an angle. And also you've got trig functions, right? Everybody's favorite. So when you see trig functions, when theta is your parameter, I want you to think about the Pythagorean identity, cosine squared theta plus sine squared theta equals what? Do you remember? Equals 1, okay? So this is where you're going to start every time you've got parametric equations with trig in them. And then what you want to do is isolate the top equation for cosine of theta, isolate the bottom equation for sine of theta, and we're going to come back and plug in to this equation here. Okay, so let's try this together. If I want to get cosine of theta by itself, what would I need to do to both sides? I need to add 1 to both sides, so this is the same as x plus 1 equals cosine of theta. Okay, and then for the second equation, again, you want to isolate your trig term. You want to get sine of theta by itself. So what would you want to do first? Let's subtract 3 first, and then divide everything by 4. So ultimately you would get y minus 3 divided by 4, and that would give you sine of theta. Okay, so now I'm going to come back to my Pythagorean identity here and plug x plus 1 in for cosine theta. So I'm going to have x plus 1, but don't forget to square it from here, right? And then plus, then for sine of theta, I'm plugging in the quantity y minus 3 all over 4. Again, don't forget to square. And that is equal to 1. Okay, let me clean this up just a little bit. Let me do one more step to see if you can identify the shape of this curve. So I like this x plus 1 quantity squared. I'm going to put this over 1 just to see if that will help you identify what we're looking at. And then what I'm going to do is I'm going to keep the numerator, the quantity squared like that, but then I'm going to go ahead and do 4 squared, which is 16, in the denominator like this. Okay, does this look familiar at all? What do we think the shape is here? So this is an ellipse, right? You've got, you're adding, as everything's equal to 1. Your major axis is vertical because your denominator under your y terms is larger than what we have under the x's. So let's go ahead and put this in Desmos and see if we agree with the graph. All right, so in the blue, I have typed in what we started with, our parametric equation. Do notice if you're in Desmos, you need to use t as your parameter, not theta. Now, this is not quite giving me the full picture. What do you think, how far do you think I need to go to get a full rotation? Think radians. I need to go 2 pi, right? And there I've got the full picture there. Now I'm also going to go ahead and graph what we got when we eliminated the parameter. Oh, there it is, same equation. And this is an ellipse with center -1, 3. Again, we have gone up 4 and down 4 to get our vertices, and then left and right 1 to get our co-vertices. I'm going to force a pause on your screen. Can you try example 4 on your own? So look through example 3 one more time, see if you can eliminate the parameter theta and get an equation, a rectangular equation, so just x's and y's in your equation. All right, so I got for my final answer x minus 1 quantity squared all over 4 plus y squared over 9 equals 1. And I went ahead and graphed it, but we've got a center of 1, 0, right? And then we're going to go left and right 2 and up and down 3 from the center for our co-vertices and vertices respectively to get the shape of our ellipse there. Of course, Desmos will graph it prettier than mine. Okay, so just as a wrap-up, if I want to eliminate the parameter of non-trig equations, so typically we're using the parameter of t there, what is the strategy? So for that, we're going to solve for t in the x equation and substitute what we get there into the y equation to eliminate the parameter t. And if you look at examples 1 and 2, that's what I'm talking about there. All right, now think about how you would eliminate the parameter in trig equations. Write down your best strategy and then check with mine. So for this, in my words, I said solve for cosine of theta and sine of theta separately, right? And we'll plug into that Pythagorean identity. So write it how it makes sense to you. I've got some suggestions there. And we will see you all next time. You do have a My Math Lab assignment over this.